Okay, we are recording. All right, so, okay. Yeah, joining seems to sometimes be difficult and sometimes be not difficult. Let me talk about this first. That's why I do the recordings. Most of you seem to do okay, but I have another student who said they couldn't join. I'm not a Blackboard expert, so besides just going to Blackboard Ultra, Collaborate, and picking the room and putting join session, I'm not sure what more there. I mean, I don't have an idea of what to do beyond that. You could try emailing Blackboard. You could try logging off, signing out, and signing back in. You could try. I had to restart my computer last day because the whole thing crashed, and I couldn't get anything to load or do anything. I had to restart my whole computer. So if you have friends who are having issues, that might help. As far as labs, so the lab that was put up is for 2 weeks of lab. It will be a long form lab, so there's no new lab for tomorrow. Basically, that's labs 2 and 3. All right. Um, and that's kind of what the semester is going to look like. Basically, after that lab, there might be issues connecting with tablets and phones. Like I said, I wish I had answers of how to do this, but I unfortunately do not. Um, so the whatchamacallit, the next lab will be the DC series circuit stuff, which we'll do. I'll assign that after spring break, and we'll have magnets and AC circuits, and then we'll have a brief optics lab. So there's not going to be, there's a lot to do as far as the labs go, but there's not a lot more, there's bigger reports to write, but not little tiny ones. So that's how the rest of the lab will go. Also, if you're having problems loading some of the simulations, like I know you might in Java, I know there's only 13 of you now, but hopefully someone will see the recording. You can type in the FET instructions, say Java help with FET, in YouTube, and a bunch of videos come up, so that should help you solve your problems, whichever platform you're on, whatever you're using. Also, it is okay and I suggest if you are in that camp, use the chat room in our lecture and find someone who does have access. And what I would do is do a Zoom chat or a Skype chat, get to know them, and work and share each other's screen and help each other with the lab. Lab is still supposed to be collaborative in its own way. However, because we're doing things with simulations, things like errors aren't going to come up so much, error analysis. But again, as I say with the lab, we're really just, we are doing the best we can. So, with that being said, I think the files are ready. So I want to start by reviewing some of what we talked about with electric potential. I know what you're thinking, which is that we could just watch the video, and I guess that's true, but I'm not quite used to that reality yet. So I want to go over some of the highlights of electric potential because it's a very key and important idea. All right, and it connects some of the work we did with Gauss's law and the electric field, and makes it, connects it to the energy that can be stored by the field, and connects it to this idea of potential difference and voltage, which helps us look at how things travel in electric fields. So, basically, oh dear, I wanted to get to our definition. Basically, we have our definition of the electric field or potential difference based on the electric field. And you'll want to note that all of this stuff is accounted for, this minus sign, and all of these other things from the energy and work considerations we did before, right? That go here. All we'd really have to add to get this part from looking at work and kinetic energy, the only connecting part we need to recall is that, that work is equal to the integral of f dot ds, right? But since we're talking about the electrostatic force, F is equal to QE, right? So this becomes the integral of Q E dot ds. And we can see by equating terms the work and the potential energy, which we have here. I don't have that. From the work and potential energy, we see that the potential energy, right, delta U, will be equal to Q times delta V. And then the work will be equal to the integral of Q E dot ds. All we're doing is using the work energy theorem here. And we that will lead us directly to the equation we looked at here. All right, basically the Q's cancel, and that's how you get it. Okay? So, I want to at least go over some of the examples we did last time again and point out some key differences. We looked at the potential for a point charge, right? You'll notice we can do this from our definition. We can use Coulomb's law and plug in our electric field, which you can see right here. And then we get this nice expression for the potential difference of a point charge. I'll write it here in the other form that you'll see me write in a little more. V equals KQ over R. Okay? And you'll notice everything makes sense, but however, I do want to point out some things some things we've seen through our electric field chapters and that we're going to see kind of going forward, which are choosing limits of integration. So we have our definition here, right, that I'm pointing to, this delta V equals the minus integral E dot ds business. But you'll notice we start at R, right, and we're looking at the potential differences, the potential difference between the point here and this being moved to infinity, right? So, so that means we start at R, that's our initial point, and we go to infinity, and we set the final voltage equal to 0 at infinity, all right? And the initial voltage equal to V at R. So we sort of create boundary conditions. The more multivariate calculus you do, the more you're going to see that this word and this term boundary conditions keeps coming up. You might have done it with some ordinary differential equation stuff, which you should have seen a little bit of in Calc 2, even though I know we have a differential equations course. You should get a little taste of it in Calc 2. So anyway, going forward, we can see for a system of particles, and remember, if you're wondering why I'm going fast, this is all review. We covered this chapter already, so I'm reviewing this chapter just so we can see it again and kind of get caught up and to see if any questions arise. So please ask questions if you have them, but keep in mind if you're wanting me to slow down and go through it more thoroughly, that I'm going to say you can watch the previous video for. So when we look here for a system of particles, all we do is add up the individual contributions and we get an unsurprising equation, right? You'll notice for the checkpoint, I wanted to point out that the potentials are all the same because there's always, you're looking at the potential of a point P. So P is the point at which you're evaluating the potential, right? That's another reason why we move that point, that test charge to infinity, because when we look at the point, that's the potential at that point. In a problem, there won't actually be a charge there. So you'll notice at P, there is no charge in either case. And there's two charges in our system, right, in each of these cases. And you'll notice that if you look at the equation up here, two charges mean two terms in the equation. And if we look at this checkpoint, you know, again, just reviewing, if we look at it carefully and look at our two terms, we can see that each of A, B, and C will have a K, right? I think they both have the same, they're both protons, right? So K, Q proton. I'm a little old-fashioned. I don't write E, elementary charge. Some people would do that, but but that's okay. So that's just the charge of the proton. Oh, in Chase, so in the book, you'll see Q proton equals E, the elementary charge, and Q electron equals minus E. I'm just getting older, and I get confused easily, so I just want to know what I'm talking about. So I'm usually just explicit with how I write the charge of the proton and the charge of the electron. There's no need for you to be if you don't want to. E and negative E are perfectly fine. Where E stands not for electron, but elementary charge. I think I would get confused just assuming it was the charge of the electron. Yeah, you might see the book write it that way. Yeah, where E is the elementary charge here, not the electron charge. They happen to be the same, but that's also the charge of the proton. You have to keep track where the sign goes, right? That's important. Hold on here. No, E is the elementary charge, right? So hold on one second. I'm going to turn on a light here. All right. I'm realizing it's starting to get dark. I think I just always had the light on before. All right, is that better? Okay. Oh no, that's not good. Is it better now? It's good now? Okay. Sorry about that. But your image is mirrored. Oh, that's gonna happen, right? That's just because I have an old camera. It'll fix itself eventually. I'm not gonna worry about my image being mirrored or reflected. I'm just gonna keep on trucking through. So sorry about the sound. But anyway, what I wanted to point out is that each of these three distributions in the checkpoint will have a term that looks like this and a term that looks like this. All right. Now you'll notice with these two terms that since there's two charges, there's each of the same two terms. And again, the potential difference is a scalar, not a vector. Therefore, when you have these two terms, you're just adding both of these in each of these pictures, and therefore you get the same net potential. And this was further seen in this particular example, right, where we looked at the electric field and the potential at the center here, and we saw that there was due to the symmetry of the charge distribution, there was no electric field at point C, but we had a potential. Now, when we looked here and moved the charges, the potential at point C stayed the same because we just have the same 12 terms that we're adding up. However, now there is a potential at point C that, and since we have electrons, right, we want to, because I messed it up, I remember messing this up last time, we want to keep in mind that we go towards the charge distribution, right? So we have an asymmetric charge distribution, so we'll have a net electric field. And I want to point that out, right? That when you change the distribution like this, as long as the terms that you're adding are the same, the potential difference isn't going to change at this point, but the field can change. All right. So that being said, we then, and I'm going to go through this part quickly because we went over these, but we essentially did what we did for electric fields with Gauss's law and Coulomb's law, which is we developed expressions for potential differences of common charge distributions. So we have our dipole right here, and we got this again, this potential difference in terms of our dipole moment. And if we see, we'll see what it is for a disk, right? We start to have to integrate up, and we looked at the line charge, right, where we got this integral that we looked up. And similarly for a charged disk, that was a line charge we had, or a 4 for a charged disk. We do it the same thing. What I want to point out is that defining dq is important here in the integral. This is sort of your main step here, right? And defining dq here and r in terms of integrable variables is what creates a manageable integrand instead of a abstract integrand. Okay. So you can see how it all plugs in here, and again, you would look this up in a table. That's, you know, I wouldn't bother trying to do these integrals by hand. Not in an integrating competition. One thing we saw is that if you have the potential, you can get the field by taking the partial derivative with respect to S. We introduced the 3D derivative, but that's beyond the scope of the class. And finally, we got to the potential energy of a charged system, noting that when we looked at the potential energy, right? When we looked at the potential energy, we would have to look at every pair in the system. So basically for a system of point charges, you'll have 3 terms. So there will be 3 terms in U here for what's circled. You would do U equals in this particular problem, Q1, Q2 plus Q1, Q3 plus Q2, Q3. Okay? There, we close that up. So that's just to, again, we're reviewing to see how it goes. If you want to see this stuff in more detail, look at the review. And there's some other stuff, but I think we're ready to move on to our next chapter, which I want to do, because I think we can cover a lot of that chapter tonight and be in pretty good shape. I do want you to keep in mind our first exam will only go through Gauss's law. So even though we're marching, even though the first exam is after spring break, and we're going to have 2 full chapters done by then, at least, if not a third, we're not going to cram all that into the first exam. We're just going to go through Gauss's law. So basically waves, charges, Coulomb's law, electric fields, and Gauss's law. All right? And that's where your questions will come from. So don't freak out about not having had an exam yet. So just so we're clear on that. So let's go to our next chapter, though, because our chapters are going to get a little more applied. So hopefully for our engineers, this stuff will seem a little bit more grounded on Earth, because definitely the last couple chapters have been fairly abstract. So let's go to Files. We'll stop sharing that one, and we'll click on 25. Okay. So now we're going to talk about capacitance. All right. So capacitance is sort of, will we have a practice test before that? I'll upload something before spring break, yeah. It won't be a very good practice exam. The questions will be similar, but you're going to have multiple choice. So that might actually make the questions easier. They'll sort of read the same, but you'll have more of them and multiple choice because the answer will be right there in front of you. So yeah. So I don't know how helpful the practice test is going to be, but I will post it. Because I have not done, and again, giving a practice test of multiple choice exams, I'm pretty limited with what I can ask. So, you know, I'm not going to post the possible questions. So anyway, let's look at capacitance, and capacitance takes place in a capacitor. And you'll notice that the base type of capacitor we're really going to talk about is this parallel plate capacitor. All right. You'll notice it has a defined area A, and the plates are separated by this distance. Now, what happens in a parallel plate capacitor is usually through some battery or some charge, one of the plates is positively charged and the other plate is negatively charged. All right, so we'll see that basically that that capacitors can either be charged or discharged. This would be a fully charged capacitor where you have separation, and you'd have an electric field, a constant electric field like this, which is much better shown here. Now you'll notice we have these edge effects, which don't add much to the problem. They're definitely a source of error. So we approximate it. We're only going to really focus on this part of the capacitor and ignore these edge effects. You'll notice the density of field lines is smaller, which means that the field is sufficiently small on the edge of these capacitors, although they are there. And the capacitance, which defines basically how much charge can be stored per potential difference, is equal to, I'm going to change my color and write it up here. So the capacitance is given as Q over the potential difference, but you can solve for Q here and get that the charge is equal to the product of C times V. And often it's written this way because the capacitance will be constant. So basically you sort of set up, you'll have a capacitor that has a rated capacitance, and you'll charge it up and discharge it. Now, I wanted to show you, there was a nice picture in the book that I put in here that shows what capacitors look like in real life. Right, C is equal to Q over V. What you can see here is various types of capacitors. Let me put on my hand. If you open up any electronic device, you will see these all over the circuit boards. Okay, particularly for any of you who have built your own computers. Those can kill, like, well, they can kill potentially, but that would be through discharging electricity through your body, not through a microwave. Microwaves are different. They resonate water cells. So capacitors charge and discharge electricity. So they're dangerous in the sense that any electric source is dangerous. And unfortunately, not being in class, we won't get to live through the very exciting moment when a student inevitably blows one up in lab. So, you know. But these are completely electrostatic. They don't transmit. We're not looking at electrodynamics yet. So we're just looking at stored charge and dissipated charge within a device like this. But this is what you would see. This is what they would look like. So moving on. But we want to look. There's a lot going on in this circuit. Okay. So if we look at so in order to charge and discharge a capacitor, we need three things. We have the capacitor right here. Capacitor. I'm cheating because it's spelt right here, so I can write it without fear. My handwriting's still bad, but we have here, this is a battery. And this is a switch. All right, so you'll notice that, and we'll start seeing this a lot more. So I'm going to delete that. But you'll notice all those things I wrote. This is what the real setup looks like. Okay? So you have, again, the battery, the switch, and the capacitor. This is kind of ugly looking. We can represent electrical circuits in what we call here a circuit diagram, a sort of idealized wiring where everything is clean. And you'll notice that all of the elements that are in our picture, again, we have the battery, the capacitor, and the switch are in this very clean circuit diagram. Circuit diagram. All right. And you'll notice that when the switch closes, the potential difference across the system is equal to that of the battery, right? We're going to learn about real ideal versus real batteries as we go forward, but we're just going to keep things simple as we introduce this idea, okay? One thing we're going to want to understand before we introduce is current. So current won't formally be introduced until the next chapter, but current, no, that's a unit vector. Hold on, I can delete all that, that's fine. But current is the flow of charge is going to be equal to dq dt, and we'll sort of look at that current flows from one end to the other. Now this is confusing because the direction of the current, as we look at it, will actually be opposite the direction that electrons flow, which is probably why they don't introduce it here. Just looking at in terms of electron flow, we can see if the switch is closed, right? Electrons will flow to this plate. Or hold on, no, that's wrong. If the switch is closed, we'll make a bigger capacitor. We'll make bigger things. The electrons will flow to this plate on the right here. And that will induce a positive charge. Here. Now the gap is real, right? So there's an electric field across the gap, but there is no, current has a hard time flowing. So if you if you take off the switch, if you open the switch, the capacitor won't discharge yet because the circuit is still open. All right? In order to discharge the capacitor, you'd actually have to remove the battery and close the circuit, so you'd have something that looks like this. Hold on. With just the capacitor in there. And now you can see if this is the case and it's fully charged, the negative charges will want to migrate and even out with the positive charges, right? So those negative charges will go out until the charge is neutralized and the capacitor is no longer charged or it's discharged. So that's basically how capacitors work, and I think I may have jumped ahead, but hopefully you'll be able to read about some things. I want to look and see if there's vocabulary here we need. So I'm not reading this to read it to you, but you'll notice they call this the schematic, right? The battery has terminals, a positive and negative terminal. That's language we're going to use a lot, okay? We have our plates, our high and low plates. You'll notice that high is plugged into plus, and the L is plugged into the minus. The distance between the plates will matter. We're going to find that shortly. Basically, it will affect the value of your capacitance and your potential difference. We're going to see that in a minute. But right now, we're just going over the basics. So I did jump ahead a little bit. But let's see terminal, positive terminal, negative terminal, and we see how they're labeled. So I think we're good there. So checkpoint one, before we go too far. So does the capacitance of a capacitor increase, decrease, or stay the same when the charge on it is doubled? And B, when the potential difference is tripled? So if you'll recall, right, Q, let's see, Q equals CV, which implies that C equals Q over V, right? So I think we have it. But you'll notice in A, if you increase Q, if Q goes up, right, C must go up. But you'll notice if V goes up in part B, the denominator gets bigger and C goes down, right? So, so increase, and decrease. Does anyone have any questions on that or not see it? Just plug it in and it should make sense. Wait, it does make sense or it doesn't make sense? I just got a no from Anthony. I forget what it was. Oh, it does? Good. Okay. All right. Good. So moving on to more fun with capacitors. Oh, right. I have this whole thing is. We now want to be able to calculate capacitance. All right. And we're going to see where the distance comes in because remember, you'll remember that V, right, which is in, so let's keep writing it down over and over again. Q equals VC. So there's room with Gauss's law to replace Q in here and get the capacitance or look at the electric field of a capacitor. All right? Now, if we look here at the potential field, we want to create some area. So we create this Gaussian surface. I want to highlight it before I delete it. So there's your Gaussian surface. Boop. And we'll delete that. And we'll notice that the electric field, you should almost be able to see that it just sort of looks constant. It goes to this value. Now let's see if it does change. There might be, your intuition might say, well, it should change as I go through, but I have an equal flux from one end to the other. Now I don't want to draw a Gaussian surface around the whole thing because then my net flux would be 0. And I'm interested in this very, very non-zero electric field. So you'll notice I have my field, but I want you to notice it's a little weird. I'm going to do my path of integration from, and I realize no one can see anything, I'm going to do my path of integration from here, the negative plate, lower potential, to higher potential. This will be a convention that we usually see and do. Now, you'll notice when you use Gauss's law, and I can't stress this enough, always, always, always start with actual Gauss's law. Always write that down because it's always correct and you're doing guesswork. Then you can draw the potential of, write the potential of this here. Now, I think one of the reasons we choose this path is because it will naturally give us a negative sign that cancels out from our definition here. But let's go forward and see how we're going to get this electric field for this parallel plate capacitor. You'll sort of notice we already did this in the Gauss's law chapter. We just didn't call them a capacitor. All right? So let's look at the let's look at the integral. You'll notice that, again, they took away the minus sign, but they're recognizing that they're going the opposite direction up here. So we're using the this expression from the last slide, right? And this gives us a very simple integral, right? The path ds from 0 to d is going to be d. And so we have from Gauss's law, hold on. We have from Gauss's law, which I'll write again because you can't really ever see that enough. E dot dA, in this case, is going equals Q. Well, I need epsilon not there, right? And we can do this integral that it was basically, we looked at this, we were able to use Gauss's law to get this E dot ds integral, and this can reduce to implies that E, when we do that integral, epsilon naught E times D equals Q. So this whole part here comes from evaluating Gauss's law. All right, where we get the electric field, and then we can look at the voltage, which has the same integral, right? This plus minus E business dot ds, and that will also be equal to ED. All right. So when we look at this, no, I'm sorry. Hold on. See, I already made a classic mistake. Gauss's law does not give us the line integral. It gives us the distance. So you can see how easy it is to mess this stuff up. All right. So we have Gauss's law, which gives us this factor here, and we have our definition of voltage will give us this here. All right. So this is EA from Gauss's law. From voltage, we have ED. Now, capacitance is equal to Q over V. Or, let's look at Q. We have epsilon naught E times the area, right? That would be the area of the plates. And then we have over ED. The E's cancel, and we get this equation here. All right. So what I want to point out to you is that you'll notice that the capacitance, right, depends on fundamentally only the, going back to the first slide, the area of the plates and the distance between them. Okay? And we can also see if we have a constant voltage, right, using our definition of using Gauss's law, which, well, this is the reduced Gauss's law, this is the reduced from the definition of voltage, and then we just use our Q over V, and we get this, we get that expression for the capacitance of the parallel plate capacitor. All right, so fun times, yeah? All right. Okay, good. Maybe everyone's the chat room enthusiasm is overwhelming. So all this, well, all this would, it depends what you mean by the Tesla chapter. We're going to learn about Tesla when we talk about magnetic fields, because the unit of the magnetic field is the Tesla. But really, when we talk about something Tesla did, we're going to talk about AC power and AC circuits. So everything ties in with that eventually, with what you would call it, the circuit stuff. Tesla will feature in our course, but it might not be in the exciting way in which you hope. So anyhow, so calculating the capacitance, or defining the capacitance of a parallel plate capacitor in terms of properties of that capacitor is pretty easy, and it is consistent with our definition, which can't ever write enough, which is Q is CV. All right. Again, this implies, I hate that button. This implies that C is equal to Q over V. And that's all we did. We got Q from Gauss's law, right? That's where we get the Q from. We use our definition of V, and then we take the ratio, and that's where the equation comes from. So All right, so now for a cylindrical capacitor, you'll notice that the same thing becomes, we do it now, but it becomes a little more involved. So here we have Q equals, we have our Gauss's law, but now with A, we have to add in this term for a cylinder, right? And now, when we have E dot ds, we need to, or for our cylindrical capacitor, we'll plug in our dr over r integral. We'll plug this in and get from our other information, and you'll notice we'll get this expression for the voltage, right, for a cylinder. So you can do that both way or either way. Right, I think they're just doing, again, a point charge, a circular. They're doing this in, they're just integrating the general expression along the along the radius, right? So there, I guess they're calling it dr as you go out from the cylinder. And essentially, you'll notice that in this case, you can get something that is quite more complex. But once you get the integral, right? Once you get all this, all you have to do is take the ratio, and again, you'll notice the electric field once again will drop out. Are they missing an electric field term here? No, they've plugged it in. Oh no, Q. Okay, so this is Q here. So this is the voltage. So they're plugging. I see what they're doing. So here, they're saying they're plugging in Q here, right? And then getting it to cancel that way. Because let me show you. So they have Q equals C over V, right? No, Q equals CV. See, I'm having a bad day with stuff here. Q equals CV. Well, let's at least get it right. So when we look here, we can look here and put hold on. No, I think they. Oh, okay. So solving for E and V. Oh, my spider sense tells me that I'm missing something here. Hold on. There's a step that's been removed. And I was just planning on talking about it. I didn't. It's always a mistake to not rederive everything. Oh, right. Duh. So, okay. So basically, they solve for E here. And let's write that in, because that would be smart. Solving for E equals Q over epsilon naught 2 pi RL. That should look familiar, because basically what you do is you plug the E in here, right? So you have this expression, and then you do what you should all along. I'm sure some of you saw it, but I was being a bit of a blunderhead. So if we have here that C is equal to Q over V, right, you just solve for Q. Right here, you have Q here, you multiply by V, because remember, you can write here that V equals Q over, it's a little lost with the stuff in the middle, but you can write this like this, ln of B over A. And here you just solve for Q over V, and that gives you C, right? So you put the V on this side, and you move everything to the other side. So you get 2 pi epsilon naught L upstairs, epsilon naught, hold on, epsilon naught L over ln B over A, and that's going to equal Q over V. All right. So the idea here is that in the cylindrical setup, you solve for Q over V, and in that sense, that just gives you the capacitance, right, from our definition. I need a cough drop because not breathing is not fun, and I don't seem to know where I put them or where my second bag is. Oh, there it is. I've been looking for this all day. So, yeah, I can write it on top. So let's make this. Let me my cough drop in first. So let's make it cleaner with a different color and try and make it a little smaller. I wish I could move it all. That would be nice. So I'm actually going to clear everything and rewrite it. Okay. So the first thing we do to make sense of this is we use Gauss's law to solve for the electric field. Equals Q over 2 pi R L, and I'll stick the epsilon naught there just because I can. All right. Now, basically, this is a little different than last time, right? Because with a parallel plate capacitor, each equation could be handled separately. Now Gauss's law, in this particular case, gives us the electric field, and we can just, in terms of R, so we can plug it into our equation here, which is what they do. So I'm not going to rewrite all that. What I am going to do is take away this middle step and rewrite, and once they do the integral, what you really have that gets lost, I think that it does get lost in translation, is that the voltage is equal to Q over 2 pi epsilon naught times L times the natural log of B over A. Now I think that is written, that very much is written on the slide, but you have these intermediate steps, and that kind of gets lost, right? So basically, what you do here is you rearrange and you solve for C over V. So basically, what I would do is I want, or Q over V rather. So remember, C is Q over V, right? And so we have, we rearrange, we just do the algebra and rearrange everything. So on one side we have Q over V, right? And then we have to move all that other crap to the other side. So that's going to be 2 pi epsilon naught L, right? And that's going to be all over the natural log of A over B, or B over A rather, sorry. I'm mixing all sorts of stuff up tonight. B over A, okay? And remember, C is equal to Q over V, so you'll notice that this equation is identical here to what we have on the bottom of the page, okay? So any questions on this? Questions, 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 questions. Okay, so I think we'll move on. And moving on. If we do for a spherical capacitor, These are the results for some other ones. I encourage you to try these on your own. They're a little hard. Again, like the cylinder, but they should be doable. So for spherical capacitor, the capacitance is given here. All right. And for an isolated sphere of charge, the capacitance is given here. Now, I want you to look at something before we do the checkpoint. I want you to look at all three of these, and I want to notice, or all four of these. And I want you to keep in mind that when it comes to all of these capacitors, for parallel plate, the capacitance depends on the physical area and distance between the plates. For the cylindrical capacitor, right, B and A are these radii, right? You're integrating between A and B. So in that sense, the length of the cylinder is L, and you have the inner radius and the outer radius. So your capacitance, again, depends on the actual physical properties of your capacitor. And you'll note it's the same thing as we move forward. Oh, I wasn't meant to do that yet. So the same thing as we move forward for the spherical and isolated sphere. Everything is in terms of the physical object for the capacitance, okay? So I think what I want to say there is it seems non-intuitive, right? When you say that the capacitance is Q over V, because it could be anything, and it sort of makes the first checkpoint seem a little silly, because in real capacitors, these are just abstract quantities that we can solve for to understand what the capacitance is in terms of the geometry of the object, all right? So this is just always true in general, and it's what you do to arrive at a result for the capacitance that depends on the actual physical parameters of the capacitor. Now let's do the checkpoint. Okay. So for capacitors charged by the same battery, does the charge stored in the capacitor increase, decrease, or remain the same in each of the following situations? So let's read them one at a time. So let's look at A first and not even read B and C. So the plate separation of the parallel plate capacitor is increased. So it wants to know, does the capacitor or does the charge? So the question here is, does the charge stored increase or decrease? Okay, so let's take a look. So when we're doing this, so if we increase the distance, let's take a look at the capacitance. So C is equal to epsilon naught times the area over the distance, I believe. Right? So the capacitance is is there. So if we look here, we also have Q equals CV, right? So as the distance gets bigger, the capacitance decreases, right? And if the capacitance is getting smaller, the charge stored is also getting smaller. So that, I would think, would be decreases. All right? So now let's look at the radius of the inner cylinder of a cylindrical capacitor is increased. So the radius of the inner cylinder, so let's look at that and know exactly what we're talking about. That means in the cylinder capacitor, this radius is getting bigger, right? So what say you there? You probably need to play with your calculator a little bit. But remember, all these arguments are in the natural logarithm. Oh, I didn't mean to do that. See if you can get it, though. So we have, so we're looking at C is proportional to ln of B over A, right? So as A gets bigger, So let's see, we want the radius of the inner cylinder is increased, right? So as A gets bigger, this ratio gets closer and closer to 1. So I would have to play with the calculator to be sure, but what's the logarithm of 0 is undefined because logarithms go like this, right? If I'm remembering correctly. Right? They're slow and then they sort of start to really jump up as you go towards 0, right? So I think ln of 0 is infinity. ln of 1 is 0. But so I think the idea is that as this ratio gets smaller, right? Because B is bigger than A. As this ratio is smaller, it would be and it gets smaller and smaller, you're going to increase your capacitance. C will get bigger, and thus the charge stored will get bigger. Yep. Oh, right. The ln gets, okay. Again, I forgot. I was looking at the voltage. The ln term is in the denominator. So the ln term gets smaller and smaller and smaller. And then, right, good job, Daniel. Right in the capacitor, it's in the denominator here. So as it gets smaller, as I was looking at it, I was looking at the function. I was like, well, wait a minute. You can't physically get more than 1, and the ln of 1 is going to be 0. So I was looking at it, going, I just saw it said it increases when I clicked forward. But now that makes sense, right? So the ln b over a term is in the denominator. That's going to get smaller, and therefore, indeed, the capacitance will get bigger as that term gets smaller, and the Q will increase. Okay? I did it again. Now, the radius of the outer spherical shell of the capacitor is increased. So if we have here, if the outer radius is B, if B increases, this part gets bigger, and we're looking here in the denominator. If the the denominator is getting the denominator is getting bigger, and the numerator is getting bigger, so this one can seem this one can seem a little harder. But I would say B times A grows faster than B minus A. So I would say that the numerator is growing faster than the denominator. Yeah? So in that sense, I would say it's increasing. Ba-bam! All right, great. So as you can see, there's a lot to keep track of. And if you go back and look at my errors, you will notice almost all of them are what I call bookkeeping errors, right? Reading the wrong equation and thinking one equation is another equation, that's a bookkeeping error. Some of my errors, my non-bookkeeping errors, are more of my dysgraphia errors, which are just writing one thing and thinking another. But a lot of these were bookkeeping errors. And I want you to see how important that is. There's a lot to keep track of. So you want to slow down and just sort of do these problems methodically. The slower you go, the less lost you'll be. And even though it seems like it might take more time slowing down, you'll save a ton of time than getting lost. Because once you get lost, you can just go around in a circle, and it's not fun. So, any questions about? Can we repeat C again? Sure. So with C, if you look here in part C, you'll notice that you have B increasing in the numerator and B decreasing in the denominator. So when you have that increasing both times and you don't want to use a bunch of you have to think mathematically what grows faster, right? So let's do it explicitly. So let's say that A is 2. All right? So when B is 1, so we'll make a table. All right, A, B, and then this will be AB over B minus A. So my claim is that the subtraction is slower growing. The numerator grows more slowly, or the numerator grows more quickly, I'm sorry, rather than the denominator. All right? So for B equals 1, for instance, A is the same all the way through. So for 1, we'll have 2, and then 2 minus, that's a terrible thing. So B can't equal 2, right? Or so we'll have B is 1 minus 2. That's going to be minus 2, right? And then for 3, because B is getting, because we're just increasing B, right? So for 3, we have 6 over 3 minus 2 is, this one actually doesn't make sense because that has a bigger value for one than the other. So, so physically 3 is actually, if A is 2, 3 is sort of our next integer. So we have B is 3 minus 2 is 1, so that's 6. And then for 4, we have 2 times 4 is 8. On top, 8 times 2, and then we have 4 minus 2 is 2. So we have 4, so that's not looking good, right? 3 times 2 is 6, and then let's do 5. 5 times 2 is 10 over 5 minus 2 is 3. Now we're starting to grow again. If we do 100, right? 100 times 2 is 200. 100 over 100 minus 2 is what's 100 minus 2? 98? Yeah. It's still, yeah, it's always still decreasing with 5. It's getting smaller. We may have to actually take a real limit here to see how this goes. 200 is 2 point something, right? So we go down to 6, and I don't know, if it's a billion, that would be 2 billion. Yeah, it's always going to sort of go with 2. 2 might just be a bad case. If it's 10, no, it always sort of converges. Huh. You know what? I'm going to switch this one to question mark. And I'm going to have you guys look at it. I'll leave it as, because looking at it, I would think that, but there's a few things to look at here. The radius of the outer spherical shell of the spherical capacitor is increased. Yeah, definitely a gold star. But yeah, we'll have to come back to this one, and someone should investigate a little more. Probably me, and we'll see. Because I definitely thought the multiplication would grow faster, but that could not be the case. That could definitely not be the case. We seem to have definitely found an exception, even if it works for almost every other A. Not necessarily so. Because it seems like each value will be about 2. And well, you will converge to this value here if you make it big enough, right? Because then if you make if you take your outer sphere to infinity, you get the isolated sphere. So I guess the real question is the capacitance of the isolated sphere greater than the capacitance of this value here, the spherical capacitor? right? Okay, so let's move on. That was weird. I'm gonna call a question mark on that one. So so now we're gonna sort of start to focus on circuits, and introducing parallel and series is sort of weird to do without talking about current, but we will try to do our best. All right? And we'll also do this after break. So let's take a 15-minute break, and let's come back at 7:06, 7:07. My voice needs a break. All right. I will leave the recording on. Is that true? All right. Fun fact during break. Let me see. I went to the book to see if I could describe the insanity. So they do something here that you often see in physics, which can be a little obnoxious. But they're saying that we have AB over B minus A. All right? So here's at least the abstract math of it. So what they do is they're dividing each term by B. So it's basically you can divide by B, 1 over B times 1 over B. All right, so that's basically multiplying by 1, and that's going to equal A over 1 minus A over B, right? Where A is our inner radius. So now this is a little easier to look at, and now we can see that as B becomes bigger, let's see what, we're at least going to answer the question. I don't know that we're going to get increases, but we'll at least answer the question. So as A becomes bigger, this whole thing becomes smaller. So you're 1, I see. So it's 1 minus a smaller number, right? So because, you know, as at B is equal infinity, for instance, right? So 1 minus A over B. This is always going to be some positive number until it gets to 0. So basically, as B gets bigger, the denominator gets bigger. Yeah? I don't think the denominator gets smaller. I think C might be wrong. Yeah. So I would think that because as B gets definitely, so look at it the other way, as B gets smaller, and it can only limit at A, right? So as B gets smaller, the denominator approaches 0. As B approaches A, the denominator approaches 0, which makes the capacitance bigger. So I think that if the radius of the outer spherical shell of the spherical capacitor is increasing, I think you're actually going to be decreasing there. I think the book has messed it up. I think we'll just cross that out. At least according to everything I'm looking at here. So, all right. Well, B is the outer radius, right? You could only shrink B. B can either be expanded to infinity or shrunk into A. And then you can't go lower than A, right? So you can't bring this past this point. You can only shrink it down physically so far before you run into A and things get complicated. Right. It says if B, yeah, it says if B is growing. Yeah, that's how I'm reading it, unless I'm missing a word. Always a possibility. I could always be missing a word. That's what I try and get you guys to watch out for. But it says the radius of the outer spherical shell, which would be, in this case, B, is increased. Yeah. Right. So A over B will go to 0 as that gets bigger, and as A over B gets bigger and that goes to 0, that makes the denominator bigger. As that gets bigger, that would, that would lead to a decrease in C. And then, yeah. So I don't know what they're talking about. If someone can find some, this at least makes sense and it's easy to evaluate this way. But other than that, all right. I'm going to go look at my dinner options, so I will be away. And again, we'll start up at about 7:08. I am back. Okay. I'm not back. I forgot the phone. There we go. I just want to take attendance very quickly. All right. Hold on. Okie dokie, and there we go. All right. Okay. So, ready to go forth and continue. So, all right. So we're now going to learn about two ways of arranging circuit elements, all right, which is series and parallel. So series is defined, again, I want to point out the circuit diagram that points to it. We have here a battery with its negative and positive terminals, and you'll notice we have three capacitors. Now, for capacitors to be wired in parallel, you'll notice that each of them, if you look at each of these points, right, they both connect, they connect to the same place, which kind of makes them the same equivalent electric point. So you'll notice that these capacitors are in parallel because they're both wired on one end to the positive terminal of the battery, and they're wired directly on the other end to the negative terminal of the battery. All right? So you can actually increase this chain, and as you look at it, you can create more branches. And if anything is wired in parallel, you must connect both of these. If these two are in parallel, they must both connect to the same place, which they do. All right? Does everyone see that? I'm going to need another cough drop. Take a look at it for a little bit. See if it makes sense. Basically, if I were wiring this, right, and I had, let's see, I had my battery with its positive terminal and negative terminal, right, and then I had my capacitors. I'd wire one up here, and then if I had another capacitor, I'd wire them up here as well, and I'd wire them up here as well, like this. Okay? Maybe that makes more sense. If you notice, as crafty as those wires are, you can just rearrange this and the wiring points to create these little junctions here. And understanding these points as junctions will be very important as we dig deeper into understanding circuits. There's a lot to unpack here, so I want to be sure before I move. I'm not moving on to the next slide, but before I move on to more of what it means to be in parallel, that we've got the basic idea of the connectors here. So does that make sense? Okay. Now, basically, when things are wired in parallel, there's the same potential difference between each of the two terminals, right? So because these are equivalent to these two terminal points, you have the same potential difference between any of the 2 points. All right, that's a consequence of being in parallel. And I'm going to clear this. So what that means is that as you look at the voltage, right? Oh, I need to get my pencil. You can write Q1 equals C1 times V1. Q2 equals C2 times V2. And Q3 equals C3 times V3. Now, remember what I said. The potential difference is the same across each of these terminals. So we actually don't need a 1, 2, and 3. We can delete these. And we'll do that. And you'll notice that that's what we have right here. All right? Now, the idea of looking at a circuit in series or in parallel or any circuit is to sort of get an idea of what's going on in totality. So the circuit stores a total charge Q, right, equal to Q1 plus Q2 plus Q3. And using these expressions, right, both circled ones, you can plug that into the expression here, and you'll get C1 plus C2 plus C3, but the V cancels out. And that should be easy enough algebra, not cancels out, I'm sorry, factors out. That should be easy enough algebra to see, right? And so what we can see here is that in the circuit, or equivalent capacitance of the circuit, C equiv is going to equal big Q over V, right? So we can look at that here, and if we multiply by V, we have this Q expression. This is what I'm calling big Q, okay? And we have V here. We can see that the C equivalent is Q over V is just going to be equal to C1 plus C2 plus C3. So for capacitors in parallel, the rule for adding them is given by this rule here. And what you're going to have to do in lab, you can look in the book and that'll give it away, but in lab you're going to have to play around with resistors, a different circuit element, and derive the rules in a similar way for how they add. All right? So basically, capacitors wired in series, these three, can be replaced with an equivalent circuit. It is not an equal circuit, it is an equivalent circuit. All right? And this type of analysis lets you solve for large numbers of capacitors. You can reduce it, or large systems, or set up equations to get, a large amount of variables. And it sort of gives you the means to do that, to reduce it into equivalent circuits that will then allow you to solve for parts of the next one. So that is capacitors in parallel. So that's an introduction to parallel, a circuit diagram in parallel, and capacitors in parallel. Okay, are there any questions on that in particular? No? Okay. Wait, I got a yes and a no, Mustafa? What's up? Oh, no, that yes is from a previous thing. Oh, that's an old yes. Okay, gotcha. All right, so now we have to figure out what series means. All right? Now, the easiest way to define series is to, again, use the idea of current. If something is connected in series, the current from one end to the next just all goes through. It does not branch out at all. Okay? So in that sense, sorry. So in that sense, it's very different because the current will branch out when things are connected in parallel. But as far as our current, no pun intended, as far as where we are now, we can notice that, again, you'll notice I'm going to draw two terminal points here. The potential difference across these 2 points must be the same. We're going to learn why and how that works as we go forward, but that's basically what we can see as far as as a series circuit goes. So basically what we see here is that we'll have different voltages across each capacitor, right? But because the current must be the same, that means that the charge will be the same. Remember, current is related to charge. Or as we said, I is equal to dq dt. This implies dq is equal to I dt. And the current, so that means that the charge is equal to the integral of I dt. And if the current is the same, right, then Q is going to be the same, and the Q will be the same for each capacitor in series, but the potential difference across each capacitor will be different. So in this case, we have that V1 will equal Q over C1, and they do that individually here, right? Now, I too have neighbors who play music. I don't know if you can all hear that, but it's ill-timed. It's not bad music, it's just ill-timed. So, let's see what we can say here. You can't hear me? Oh, you can't hear the music? Or you can't hear me? Oh, okay. Well, then I think we're okay then. I can hear it. My bat-like ears. So the total voltage here will be the sum of the individual voltages V1, V2, and V3. Okay? And you'll notice that with this new form, we have V is equal to Q times 1 over C1 plus 1 over C2 plus 1 over C3. We've just factored out the Q's from the above expressions here. Okay, everyone sees that? And now we can say that C equivalent, again, is Q over V. So you'll notice you move the V to this side, and you have to take all this stuff and put it over here. All right? So this can seem a little daunting, just putting all of this here. Basically what you get is that 1 over C equivalent, or C equivalent is equal to 1 over this whole sum, or to make it a little more compact, you have this thing, which is that 1 over C equiv equals 1 over C1 plus 1 over C2 plus 1 over C3. Please keep in mind here that you will have to find common denominators and add fractions. There is no way around it. All right? Now, I want to go through kind of a quick example. So what I'm going to need to do is share a whiteboard. And we're going to go over it conceptually, but you can follow it in your book. That's not the right thing. Hold on. Share blank whiteboard. Okay. So I want us to consider a circuit. Actually, I think it'd be more useful to draw the lines. I just need, no. Hold on. I just need a minute. It might take me a couple minutes to draw the circuit, but that's okay. I'll just do the best I can. Hold on. Okay. Not my greatest drawing in the world, but it fits the needs. So this is a battery. This is C1, C2, and C3. Now, I have some questions for you all. Which one of these capacitors are in series and which ones are in parallel? Okay. Let's make sure that's true. So C1 and C2, they both connect to C3, and they both connect to the positive terminal of the battery, so that looks good. Ah, yes. So C1 and C2, you'll notice that C3 is neither in series nor parallel with C1 or C2 individually, but we can make a equivalent circuit here. No. Hold on. Again, might take just a little bit. Again, not perfect, but you get the idea. And here, this is C1 or C12, as we would call it, all right, which is an equivalent capacitance after you add these ones in series, okay? And after you do that, you get this equivalent series, and the combination C1 and C2 are in series with C3. Good. Now you can also then make this now into an equivalent circuit. With the battery and one capacitor, where again, this is the battery And this is C123, and C123 is C equivalent. All right, and you would use your the methods of adding capacitors and things like that to figure out individual charges and things. So when you look at this, oh, it could get so much worse. So basically, an example would be you were given, say, everything about C1, the charge for C1 and C2. A question might be find the charge on C3, right? So what you'd have to do is sort of analyze and shrink the circuit until you could massage it to get what you want. Sometimes it'll ask for the voltage across C2, stuff like that. But you can always analyze it doing the same thing, which is getting an equivalent circuit and figuring out what you know and don't know. And then as you figure things out, unpacking the circuit back the other way. Or hold on. So you bring the circuit down and then unpack it. And by the time you're done with the new stuff you find as you pack it up, you'll be able to figure out everything you need as you unpack it. And that's how you solve those types of problems. So, questions, concerns about that? Does it make a little bit of sense? It doesn't make sense, or you don't have questions. Good. If you'd like to see this example done, I want to recommend you go to your book, and let me see what page it's on. It doesn't really give me, oh yeah, no, it gives me pages. So on page 726, there's a nice analysis of this circuit. It'll ask you a question, it'll ask you a bunch of things to do, and it'll show you how you solve for everything. So, so yeah, so that's kind of a fun problem, and it's the exact same thing I wrote. And I'll repack and unpack it. All right. So let's wrap up this chapter, and that's all we're really going to do tonight. If we finish early, we finish early. I'm not sure we will, but we might. Hold on. All right. Yeah, sure. No problem, Lewis. Share files. Share now. I'm just going to go here. It's easier to click through. Okay. We might not finish early. I forgot about energy. Thought we were moving on to dielectrics. So, one of the things we'll want to know, sort of bring this back to the abstract, is how much energy can be stored in an electric field. And capacitors kind of give us the machinery to do that. All right? And so, the potential energy of a capacitor, because you'll remember, right? So let's go back, and we remember that delta U equals Q times V, right? So in a capacitor, C equals Q over V, or And we have Q equals CV. The last one we didn't look at is V equals Q over C, right? So we can just plug that in into our expression here, and we get delta U is equal to Q times Q over C, right? And we seem to be off by a half. The half must come from some sort of integration. So I'm going to say I'm going to cheat knowing calculus. It's not great, but you're gonna groan when I do this. I'm going to say that du, and I think this is actually right too, that du is equal to Q dq over C from our capacitance relationship. And now when you integrate this up, you're going to get Q squared over 2C. Ha! See? I'm awesome. And it's pretty simple using your definition of capacitance to go from this equation to this equation for potential energy. And and so this is the work required to charge a capacitor, and this energy can be associated with the capacitor's electric field. So U is the potential energy, right? So remember, du is equal to Q dV, the change in potential. That's it. It's awful because I don't have good handwriting. So the V, these both look the same, but they're not. This is a V, and this is supposed to be a U. Yeah. So, and that just comes from our original expression for electric energy. Now, the potential energy of a charged capacitor may be viewed as being stored in the electric field between plates, right? If you read your start comment, this is one of those big physics ideas. And in the vacuum, the energy density, which is the energy per unit volume, in a field of magnitude E is equal to 1/2 epsilon naught E squared. We're not going to derive this particular equation, but you can see that looking at a volume of space, you can get an energy density of that space in terms of the electric field. So that's pretty cool, right? That's energy stored by the electric field. And again, as I sort of mentioned, to sort of relate back to what I said earlier, fields allude to, fields are sort of become fundamental objects in physics. People have tried to get rid of them, but it's not been successful. Okay, so now we get to capacitors with a dielectric. A dielectric is just something you sort of slap in. So the capacitors we've looked at all have nothing in them, basically, a vacuum or air, and so the dielectric constant is 1. But you can slap in something here that kind of increases the capacitance in this dielectric material. And it's defined by this integer kappa. It's like a dielectric constant. By isolating capacitor, the effect of the dielectric is to reduce, so it reduces the potential difference, but if you have the same charge, that would increase the capacitance. So with Gauss's law, we're not going to do a lot with dielectrics. It's really something you do in intermediate E&M. And you can sort of see the atomic view. You get I usually put an insulator, a neutrally charged object, but again, that would align these charges, induce these charges. Pretty much anything can be a dielectric material. There should be a list in the book, a table of dielectric materials. There's some specific ones that can really enhance the capacitance, and others that aren't. It just depends on how many, the density of how many ions or electrons they have that can sort of go like this and create this these fields. the field line of the atoms are in these dielectrics to create this where you have the plus charge, the pluses here, or the minuses here, and the pluses induced here. With Gauss's law, it makes it simpler to sort of see because the setup is the same as without a dielectric. It's just k is equal to 1. But now you have this constant value, and everything sort of works just like you think it is. The electric, once you can multiply kappa by the electric field to get this quantity called the electric displacement. Gauss's law, you'll notice, is cleaner. It gets rid of and sort of eats this epsilon. So one of the reasons people like to introduce dielectrics is to introduce the electric displacement and to have this much cleaner version of Gauss's law. That's all I really kind of want to say about them. That's it for this chapter, so we can go on to homework because I'm done with lecture material for the day. So yeah, we will on Thursday cover chapter 26, and we're just sort of moving right along. So so let me see if I can find in the book, because they should have a table in the book to answer say this question. Okay, so air, polystyrene, paper is one, Pyrex. Basically, I think anything is a dielectric, but some things have really high dielectric values. So polystyrene, for instance, has a dielectric constant of 2.6. Pyrex is 4.7. But water, for instance, has a dielectric constant of 80.4, and titanium ceramic is 130, and strontium titanate is 310. So you can pick materials to really boost up that dielectric constant if you so choose. And the table's on like page 731 or 732. All right. So I'll stick around until basically 8 o'clock to answer homework questions. If you have a question, let me know. I'll probably work it out on the whiteboard or something, but otherwise I took a picture of the attendance, so you can go. Yes, Isabel. What is the formula for a larger ring if the net electric field at P is 0? I'm not sure. The formula for what? For what of a larger ring? For the capacitance? I'm not sure I understand your question. So I'll go back to the larger rings. That's where we discussed them. You can turn on your microphone if you want, if you think it'd be easier to say it. So the net electric field really can't be 0 because we have charged particles, and we're always going from one to the next. I'm not sure where you're finding. We don't have electric field outside, but I'm not sure I understand your question. Is this the right question, Isabel? Right figure? That's what you're talking about? If you're talking, I can't hear you. So I'll say that. So I'm just waiting. Let me see here. Yeah, okay, so I see your mic is on, Isabel, but it's not, I'm not seeing it light up. So there's a section, if you go up on the taskbar, I was able to sort of solve this. If you click on the, if you see there sort of should be a blinking, like where the lock is on the, in the web browser on the top where you like type in web addresses. You can look at the additional permissions, and you should be able to put something in there that lets you. That's how I fix this problem. I don't know if that's your particular problem. So, or you can type it up. Question 30 for homework 2. Okay, let me see what that is. All right, I just need a minute to see what in the world I asked. Homework 2, which homework question 2, homework 2? Let me go back here. Okay, that's not an electric field question, it doesn't look like. That's a Doppler effect question. So, question 30. Oh no, this is question 30 from homework 2. Okay, hold on. That's a different question. Let's take a look at what's going on there. I need to get on the right question. Question 30. Okay. All right. Well, let me see. Okay, that's all right. So this figure shows two concentric rings at radii RS and RL that lie on the same plane. Point P lies on the central z-axis at a distance d from the center of the rings. The smaller ring has a uniformly distributed charge QS. What is the uniformly distributed charge on the larger ring if the net electric field at P is 0? State your answer in terms of the given variables. All right, so it looks like when we do this, we have, all right. Hold on. Let me get, I'm trying to get back to you guys. This isn't working. Okay. All right. For those of you who are leaving, I'll see you Thursday. And for those who are staying, let's take a look at this problem. So let me, okay, let's look at it. So let's go to a whiteboard. Okay. So we have, this is not going to be great, but we have two ellipses or two rings, one ring, another ring. Let's move this ring. So we basically have something like this. Right, we have an axis up here, and we have a point P. Right, so we have one distance and another distance. Okay? So the figure shows two concentric rings of these two radii that lie on the same plane. Point P lies on the z-axis at a distance d from the center of the rings. So what is the uniformly distributed charge density of the larger ring if the net electric field at P is 0? So basically you have two things going on here, right? You'll have some charge in one ring and some charge in another. And you'll notice you have sort of here this R, what do they call this? We can call this little RL, and then little RS. Now what I want you to do as you go back through this is you'll basically be able to find that the net electric field, so at P there will be electric field to both of these, right? So there will be ES and EL. Now you can treat each one of them as an individual ring, okay? And basically what it's telling you is that you'll be able to add the electric fields such that there will be the electric field from one ring. Oh, you're not going to be able to see that. Let's do this in a different color. So basically at point P, you'll have the electric field from one ring and the electric field from the other, and it'll equal 0, like that. So my hint to you, we'll make them different colors. My hint to you is that we developed how to find the electric field due to a single ring of charge, right? So you can look at this compound ring problem as two separate rings. One ring, right? And then you're going to want to add them. Right? You're going to want to look at when is E equal to ES plus EL equal to 0, right? So you're going to have to figure out, at the very least, when are the magnitudes the same? And then you're going to have to pick the charges, whether they're positive or negative, to figure out which the charge of the charge of the ring. Okay, so go back and try and look at it and do them one at a time. Does that help a little bit? Does that give you some? Hopefully, did you try that and that didn't work, or? Okay, so what went wrong? Because when I'm looking at this, things should be in terms of these. Remember, these are your RSs and RLs. So keep in mind your given variables. You want everything to be in terms of your Qs, right? Because it says distributed. The small ring has a distributed charge QS, so that's that's given. We want the larger ring QL, right? So we have QS, we have D, and we have RS and RL. Your answer should only have these variables in it. All right? So QL will be a function will be a function of these variables, and that's it. So I want you to, the first thing I want you to do, Isabel, is review your work and see if you're, And I think you'll see very, very cleanly that you have a bunch of other symbols in there that are not just these. But I'll give you that hint. You should only have those symbols in there. I mean, I'm looking at your answer right now. I see a bunch of stuff in there, so I don't want to go over it, but that's an old I did. Right, okay. Yeah, try again and keep everything in terms of those symbols, and I think you're going to see that it should work pretty well. You're welcome. Okay. Let's see here. Yeah. Let me see which one that is. Homework 2. He said number 13. Chapter 2. Okay. Okay. So it says the figure shows a proton on the central axis through a disk with a uniform charge density due to excess electrons. 3 of those electrons are shown. Okay. 1, 2, 3. At the disk, and the electron E at the opposite side of the disk. At R equals, so they give you a value for R from the center. The proton is initially a distance Z equals blah from the disk. At that location, what are the magnitudes of the electric field due to the electrons EC and the net electric field due to the electrons ES? Okay, so it wants 2 things here. Right, so first you do the electric fields and the point particles. So I'm going to clear this here. Right, so we can just use Coulomb's law, I believe, for chapter 22, which is that so if we have the, I'll try and do it as well as possible. We have this, and we have that, and we have a proton. Oh, so we have a proton here, and we have two electrodes. So a central, they're the center of this, and at the sides of the disk. It's weird. Okay, so A, it wants the electric field due to, so at that location, so it wants to know so we want to know the electric field here, right, at the proton. So E is equal to K Q over R squared, right? So if we look at this here from Coulomb's law, we want the magnitude, we just want the magnitude, so that should be K times this Q over the distance squared. So you would need, so they're saying it's a circle, so this is R, R, and R. I think you should just be able to plug that in. Yeah, I'm not sure why that would be wrong. Did that not? Remember your values here. You have keep in mind that if you're going to use, the only thing I could see that might have messed up here is keep in mind that R is equal to 3.97 centimeters, which equals 0.0392 meters. And you have to use meters if you're going to use K equals 9 times 10 to the ninth, right? That's an absolute. And then remember that E is equal to 1.6 times 10 to the minus 19th coulombs. That should all work. I don't know what. Did that not work for you? I would say be very careful with your calculator. It should probably, just by looking at it, be something on the order of 10 to the 7 or minus 7 or minus 8. Just, I don't know if that helps. Any other questions? All right, I'm going to stop recording.